Good morning, everyone. Today we are going to be starting chapter 16. We're going to spend about 2 days on this. Let's see. So we're going to start off with the couple of reactions that deal with different types of additions. So we're going to deal with these, what are called 1,2 versus 1,4 additions first. There we go. Okay. And we're going to talk a little bit about double bond stability. Something we really haven't discussed too much when it came to radicals, because radicals kind of just do whatever they want to do. When we're dealing with actual double bonds that have resonance to them, so let's say we add in something like we're going to take a diene system. So we have a system with two double bonds. This is referred to as a diene. Literally diene, two, double bond. If we add this in solution with HBr, this is going to pick up a proton. It's going to do what we kind of expect. It's going to form that, put the H on the less stable center and the plus on the more stable center. When we have resonance, the more stable center is always going to be the position that is next, that it has resonance. So a plus here has resonance versus having this H over here would not if we switched them. From this point, we are going to be, depending on what we're doing, talking about the difference between double bond stability and carbocation stability. So typically when we think of carbocations, we would think primary is our less substituted, or sorry, our least stable, followed by secondary, followed by tertiary. Once we start getting into resonance, these rules are going to kind of fall apart. And that is going to be because double bond stability is actually going to trump the carbocation stability. So in terms of double bond stability, we have another chart here. So our least stable double bond would be just ethene, followed by having one substituent off of it. Technically, cis is less stable than trans, although we're not going to really get too much into that. followed by having 3 substituents, followed by having 4. Why can I not draw? Yeah, there we go. Okay. With this in mind, we've got kind of 2 conflicting points happening. When we look at our double bond stability for this up here. So currently, we have a carbocation that is on the tertiary position. It has resonance to this double bond. The double bond has, so if I look at these, I'm just going to kind of label them by the number of substituents on them. So this would be like primary, secondary, also secondary, tertiary, quaternary, 1 substituent, 2 substituents, 3, and then 4 here. So we have 1, 2, 3 things coming off of this double bond. The 4th would be a hydrogen, but we don't count hydrogens. So this is a tertiary double bond here. When we do our resonance, now we're gonna have a different system. So now our double bond has 4 bonds to it, but our positive only has 2. It's a secondary carbocation. And this is where we get into this concept that double bond stability is going to trump carbocation stability. So because this is more stable, it's going to lead to the product. So they don't really care this is a less stable carbocation because it's a more stable double bond here. So I'm kind of running out of space. I'm going to delete some of this carbocation stability. Our product is going to be called what is a 1,4 addition. And I'll go through what that is in a second. Just really, BR is going to come in. And we've added 2 opposite sides of this ring here. So let's talk about 1,4 versus 1,2 addition. And then how to actually calculate a 1,4 addition. So I'm going to take a slightly different example, kind of walk through it slowly. Okay, we have a different diene here. We've got 2 different double bonds. If I look at all the centers on them, my double bond on the right here has 2 secondaries. My double bond on the left has a secondary and a tertiary. So it's more likely. Oh, the other thing is that you're always going to form your carbocation in between the 2. So in the, I don't know, allylic position. So I brought a different example. If I add an HBr, my double bond will always, or my carbocation will always form like this. I will never get so there was an H here. This kind of configuration where the positive is not able to do resonance. So this can move in. This is isolated by itself. We're always gonna, looking at this one at the top, you would either make your carbocation here or here. It's never gonna form on these two outside positions because if it did, they would have no resonance, which is automatically less stable. We're still following Markovnikov rules where we're trying to make our most stable carbocation. Okay, so we're really just picking between these two. And we are going to go looking at them. One has a tertiary center, two does not. So we're going to pick up that H on our left double bond. Actually, red is fine. We would form a carbocation where the plus is in between the double bonds here, HB over here. And at this point, we're comparing our double bond stability. So we said in the previous page, like carbocation stability is going to get trumped by double bond stability. So we might as well not even look at it. We might as well just look at the double bond stability. Currently, we have two substituents coming off this double bond. You could call it secondary. Oops. When we do resonance here, shift over this double bond to the positive center. Nope, that's the same thing. Now we have a double bond with three substituents. We have one here, and one here. One H remaining. So this would be the more stable. Because of that, this one's going to lead to the product. So BR can come in. Attack at our carbocation. And give us our product. This is referred to as a 1,4 addition. The reason for that being, if you are counting the double bond system, you could say this is carbon 1, 2, 3, 4 here. You've added hydrogen to position 1 and position 4 here. So all of this is happening at usually elevated temperature. So I think your book says around 40 degrees Celsius is when this occurs. A 1,2 addition is going to be where we do this in cold temperatures. So something we never really talk about is that resonance requires some energy to it. Typically at room temperature or a little bit above room temperature, this easily happens where you can do this kind of resonance. But if we take the same concept so we add an HBr, and we do it at something like minus 78 degrees Celsius. This is going to be so cold that resonance doesn't exist. We're just going to pick up this proton here. At this point, again, too cold for resonance, so Br is just going to come in. Attack at our positive, and we're going to get what's called a 1-2 addition. So 1-2 because counting carbons 1, 2, 3, 4, we've added H and Br to carbons 1 and 2. All right, so to kind of summarize, and we'll do a couple more problems with this before we move on. If I put an HBr at negative 78 degrees, that's a percentage sign, 78 degrees here, I'm just going to generate what I would kind of expect from this. I'll make my most stable carbocation, which forms here, and that'll directly lead to a product. At higher temperatures, we can pick up the proton at which point we have to consider resonance. So with resonance, this double bond here is more stable versus this tertiary one versus the secondary one. So this would lead to our product. Where H added to position 1 or Br added to position 4 here. Okay, I'm going to draw out an example, have you guys work through them, give you guys a few minutes, and then we'll talk through it together. So I want you to do this example here with HCl, same concept, just chlorine, at both negative 78 degrees as well as 40 degrees. So I'll give you guys a few minutes to work through this, and then we'll talk through it together. Okay, so let's take a look at this problem here. First thing we want to do is take a look at both our double bonds. If I was to make a carbocation out of the left one, so I'd either be making a carbocation in this position here or this position. We always form it between the two double bonds so that they would have resonance. Ooh, not blue. So it'd either form this or this here. So tertiary carbocation versus a secondary carbocation. In our initial step, we're going to favor the more stable carbocation. So this blue pathway here would be better. We're at minus 78. So we will not be doing any sort of resonance. This is just come in and directly attack. And lead to our product. At 40 degrees, we're going to have to consider some different things. So we're going to form that initial carbocation the same way we just did. And now we have to look at its resonance structure. So between this carbocation, sliding our double bond over, and this carbocation here, the double bond and the one on the left would be considered primary. The one on the right here would be considered tertiary. So this one is more stable. And therefore, Cl can come in, attack at this center to deliver us our 1,4 product. Are there any questions on these reactions? Okay, we're going to move past these and we're going to talk about a reaction that's called the Diels-Alder. And we're going to spend the rest of the day talking about it. Oh, I think it's IE. The Diels-Alder reaction is what's referred to as a 4+2 cycloaddition. And simply put, it's going to be 4 carbons plus 2 carbons forming a 6-membered ring. It will always consist of 2 parts. The 4 part, which is the diene. So as we talked about previously, a diene is something with 2 double bonds. Di for 2, ene for double bond. And what is called a dienophile, which is really just a double bond. Let's put a substituent on there. So just a carbon here. What we are going to have happen is our diene is going to attack this dienophile. The dienophile is then going to attack the diene. It's going to shift this double bond down one, and we are going to make a 6-membered ring with a double bond. That looks like this. I'm going to give it some stereochemistry and a plus minus. But you could also just draw a line there for this one. So this is our simple Diels-Alder reaction. These are going to get progressively more and more complicated as we talk through them. You're always going to make a 6-membered ring. And it will always have a double bond. So let's take a more complicated one. Not dramatically, but just slightly. So we have our diene here, and let's make our dienophile cis. Let's make them ethyls. So we have an ethyl on either side, or the same side of our double bond here. When we do our Diels-Alder, we're going to make a 6-membered ring with a double bond here. We will do that literally every time we do this reaction. From this point, we need to draw on these two ethyl substituents. Because we started with a cis double bond, we're going to end up with a syn product. So these are going to end up either both on wedges or both on dashes. Just put the regular bond there. And as you can imagine, if we did this with a trans double bond, this is going to lead to a trans product. So still a 6-membered ring. Double bond here. Now our substituents are going to end up trans to each other. All right. Let's start getting into some slightly more complicated ones. So these are pretty straightforward. Cis leads to syn, translates to anti, or trans, depending on how you want to think of it. I'm gonna make these a little bit more asymmetric. So we're gonna add a methyl group. Oops. To this diene here, and then we're gonna make them not symmetrical here. So we had ethyl on top, methyl on bottom. In the first part of this, well, so we're gonna do what we normally do. So we're gonna have this attack, double bond moves down, make a 6-membered ring. with a double bond here. Our methyl from our diene is still in an sp. That's not really supposed to be okay. It's still sp2. It doesn't have any sort of stereochemistry to it. We started cis here, so we're going to end up with a syn product. Nothing overly complicated about this. The part where this starts to get tricky is that because these are asymmetric here, there's no reason that this will happen as opposed to, I'm going to flip this one over. So I'm just kind of flipping it like a pancake. Now the ethyl is on the bottom, the methyl is on the top. This can do the exact same reaction. We'll make our 6-membered ring with a double bond here. Now our methyl is on top. Ethyl is on bottom. And this also gives us a product. So for this top one here, this has 2 major products to it. Like so. We can do a trans version of this. So if you flip the diene as well, you'd end up with this, which is the same thing as this. It's just flipped over. If you flip one of them, you'll get a different answer. Like regiochemistry wise, you flip both of them, you end up getting back to the same thing. So this is just the same thing as the plus minus version of our first molecule. So you could flip just the diene or just the dienophile, but if you flip both, you'll end up getting back to the same thing. All right, let's do a trans version of this. I'm gonna just add some extra stuff on there to make it so we have kind of just a lot of extra, I don't know, spinach on here. We're still doing the same reaction we always have. Gonna make a 6-membered ring with a double bond. This is, because it's trans, gonna lead us to an anti-product. And again, we can do the same thing. Flipped over. This will lead to our other product. like so. And essentially we're just flipping this part of our molecule. Which makes sense. Our molecule came from two different halves. We have a diene half and a dienophile half. So the diene half being this in blue, or sorry, dienophile. The diene half being this in green. So our green half, we're keeping the same. Blue half, we're flipping over. Let's do the triple bond version of this and then take a break, and we're going to come back and do some more complicated ones. So triple bond one is actually pretty easy, as all things go. If I instead use a triple bond here, as we always say, a triple bond is made up of two double bonds. So we're only going to interact with one of the two. The other one's just going to remain as it is. We'll make a six-membered ring. With the double bond, we only used one of the two double bonds from our triple bonds. The other one is still there. And then these two substituents can be coming off of it. Because they are sp2 centers, they don't have any stereochem. But like with the triple bond, or sorry, like with the other ones, because these can be asymmetric, there's no reason we're doing this interaction and not this interaction where we flipped our triple bond over. And this can lead to our other product, which is essentially the same thing. We would just have the diene and the dienophile portion flipped. Okay, this is a pretty good place to take a break. Let's meet back here at 10:05, and we will get working on some more complicated versions of these. So I will see you guys in about 8 or 9 minutes. Someone asked, will there ever be 3 products or just 2? We will talk about that when we get to the next portion of these. So there can be up to 4 products, and we'll talk about when that happens. try to make some wrinkle. All right, so we're gonna get back into this. We did kind of the easy version of the Diels-Alder. Now we're gonna talk about the more complicated version of it. I like to teach it through bicyclics first and then get into the more stereospecific ones. So we're going to start off with that. I'm going to take a diene and we're going to add an oxygen to it. So we're going to turn it into a 5-membered ring. And add the, I don't know, a cis double bond to it. And the way that this reaction works, I'm going to try to draw this in 3 dimensions. Is that when these two interact, they're going to try to position themselves where their substituents basically face away from each other. So it's going to kind of shuffle this top oxygen here kind of up and away, and it's going to keep these two ethyl groups kind of pointing down and out of the way. So when this comes together, does its normal Diels-Alder, we're going to make a 6-membered ring with a double bond. This bridge head from our oxygen is going to get shoved upward. And then the 2 ethyls are going to end up in the away direction. This is the 2-dimensional version of this. There's also a 3-dimensional way we can draw this, so it's kind of like a boat form. We have the 5 carbons from our diene. And then those 2 ethyl groups are going to be pointing downward in kind of like an axial fashion. Let's take a look at the trans one. Let me get rid of this portion of it. Let's get rid of the oxygen. Let's just do a 5-membered ring. Now it's going to be harder to control on this portion because they're going to be both or anti to each other. We're still going to get a bridgehead that's going up though. So we could draw this in 2 dimensions like this, or if we drew this in 3 dimensions, it would look something like. So here's our 6-membered ring with a double bond. We have a 1-carbon bridgehead. And these two, one of them's going downwards in kind of an axial fashion, and then the one that's going up would be in kind of a cis fashion. I guess I have them drawn. Oh, I'll make them look the same over here. Okay. You don't have to draw both of them. You can just draw whichever one is easier for you to see. For this next one, I'm going to require you guys drawing it in the 3-dimensional version. But for these 5-membered rings, I don't mind which one you do. If we have a 6-membered ring, there's not really a great way to represent this in 2D. So we're going to have to draw this in 3 dimensions. So we're going to make our little boat. Now we have a larger bridgehead. So we have 2 carbons here. Let me draw this the other way. As well as this 2 cis bonds here, or cis ethyl groups here. We could again do this with trans. Let's throw a, I'll do it that later. And this can lead to a trans product. Okay, so with this in mind, we are going to use a similar concept, but not use rings. So people typically get this concept. So we're starting with this here. We're going to end up pushing this middle part up into our bridgehead. The other half of our molecule ends up kind of going downward because that's going to be favored to kind of get them away from each other. And we would get this structure here. If we break the ring into 2 halves, widen it a little bit. we're going to get the same configuration when we do this reaction here. So when our diene comes in, it's going to push these CH3s up and outward, and it's going to make these ethyl groups here go downward. So we're still going to make a 6-membered ring with a double bond. Those two CH3s, we were drawing them in the middle as wedges, but that's kind of an odd way to do them. So we're actually going to draw them on the outside. And then these two ethyl groups are going to form on the inside here. Okay. So because those CH3s are on the outside, that meant that these hydrogens that we didn't draw are actually on dashes. And they got pushed downward. And this is going to be our general concept. We're going to try to keep our diene file always going down in the down position if we can. If it's trans, you don't kind of get that ability, but for a cis one, you do. These two outer positions are always going to end up as dashes. The inner positions are always going to end up as wedges. So let's take a molecule like this here. We're going to make a 6-member ring with a double bond. Our dienophile portion is going to end up being dashed. And then everything that's in the middle so that would be the CH3 and this H are going to get pushed upward. We only really care about the CH3. So that'll end up on a wedge. And then the things that are on the outside, this H, this CH3 over here, are going to get pushed down and end up on a dash. All right, I'm going to give you guys one of these to have you kind of give it a shot. We'll see how it goes and then talk through it. Okay, take about, I don't know, till 10, 20 to try to do this problem, and then we'll go through it together. It should only be still one product for this one because of plus minus. Okay, so we're gonna make a 6-membered ring with a double bond. Our dienophile is going to get pushed downward. Our substituents that are in the middle are going to get pushed up. So this ethyl group here is going to end up on a wedge. And then the ones that are on the outsides, this methyl and this ethyl, are going to end up on dashes. And that is going to give us our major product for this here. This is also referred to as an endo product. There's something called an exo product, and that is going to be where we switch the stereochemistry of our dienophile portion. So just this here, if this decides to come in from the other angle, where those are pointing upward, we can get what's called an exo product. We're not going to spend too much time talking about these. So this portion of our molecule is untouched. We can get a different diastereomer where these are coming in from above, and this is referred to as an exo product. I'll give you guys a second to finish writing this down. Okay, so now these can get more complicated, unfortunately. Let's make it asymmetric. So we're going to take the same thing. Wait, what did I have? Ethyl on top, methyl ethyl on bottom. I don't know, something like this. And this here. So we're going to do our same reaction. We're going to form a 6-membered ring with a double bond. Our dienophile portion is going to end up going away. The part of our diene that's in the middle is going to get pushed upward. So this methyl group here should end up on a wedge. Everything on the outside is going to get pushed downward. So these two ethyls are going to end up as dashes. This would be our endo product. We could also draw an exo product where we invert the stereochemistry on this portion of the molecule, the portion that came from our dienophile. To get an exo product here. Now, like before, there's no reason that we made this product and that this didn't flip over. And have instead this interaction here. So this can lead to both an endo and an exo product. They're going to be almost identical to these. We're just going to flip these two positions. So I'm going to start by drawing out the diene portion of the molecule. This here hasn't changed. Now we have the methyl on the top, ethyl with the carbonyl on the bottom. This can also have an exo product. Where our dienophile portion flips to wedges. Our two endos are going to be the major products. Yeah, endo is always major, exo is always minor. So at least there's that. Exos are going to be minor. So for this here, there'll be two different major products, like so. These are about as complicated as it gets in terms of stereochemistry. There is one more topic we're going to talk about when it comes to these. But first, let's do some triple bonded ones. They're a little bit easier because you don't have any sort of stereochemistry on your dienophile portion. So if we take the same diene, interact it with a triple bonded dienophile, we'll make a 6-membered ring with a double bond. We'll still have a double bond over here. Our diene portion doesn't have any stereochemistry because it is sp2. And then we're following the same rules as before. So the things that were on the inside get pushed up. Stuff that's on the outside get pushed down. So the methyl gets pushed up. And the two ethyls get pushed downward. We can again flip this over to get our other product. Where the carbonyls on the bottom and the methyls on the top. Okay, so the last thing we're going to talk about with these Diels-Alder reactions is going to be resonance. So if you have resonance on both molecules, both the diene and the dienophile, you're going to be able to eliminate one of these possibilities. And I'll talk about why when we go through the first one. So we're going to take a really simple example. Like so. Typically, who would think we can have this interaction here and make a 6-membered ring? Carbonyl is going to be going down. OMe is on the outside, so it would also be going down. Like so. This would be our endo product. We could also have an exo. Similarly, we could flip over our carbonyl. So there's technically an H here. Getting it on the bottom. And then same thing with the endo product. Or sorry, exo product. Like so. Now, because of resonance, we are going to be able to do is we're going to be able to eliminate one of these sets of possibilities here. So I'm going to redraw my diene here. There are two resonance structures we can make from this. We can have our electrons come down, kick out this double bond to this position here. And again, we can move this one more time down to the end. There's also a resonance structure we can do with our diene of file here. I'm just going to redraw. And that resonance structure is where we push the electrons up. And get this what our ionic species where we have a plus and a minus. Okay, if we line these two up next to each other, the negative is going to want to attack the positive. And that makes sense. That's like our normal mechanism. This comes and attacks here. That's what we think about up top here. That bottom is going to come over and attack this positive. So that makes sense. This lines up well. If we draw the same thing for the other possibility, these like lower ones down, oops, here, this really isn't going to want to come in and attack at this center. It really just wants to attack where that positive is. So this is not going to form versus that top one, which will. So because our charges aren't aligning, we're only going to get this product up here. And we're going to do a couple of these. So we'll talk about this a few times. And then I might give you guys one to try to do on your own. So taking a look at this, we got our charges to line up in this position. So it led to products where both the carbonyl and the OMe are on the top, versus when we had them staggered here, our charges never aligned. This negative didn't line up with the positive, it lined up with a double bond. So that was less likely to form. All right, let's just break down a whole another one of these again and see how it goes. Okay, so I usually just like to draw out the 4 possible products first. We're going to be making a 6-member ring with a double bond. We get a methyl here that's not going to have any stereochemistry. It's sp2. Dienophile on dashes. We've got a CH3 that's in the middle here. This one's going to end up with a wedge. And then our OMe and the other CH3 are going to end up on dashes. We can flip the stereochemistry here to get our exo product. Our other not diastereomer, constitutional isomer is going to be where we flip this around. So we can kind of just start out by drawing the same thing we have on top for the diene portion. Our dienophile, we're going to flip it now so this carbonyl on top and the ethyl's on the bottom. Our last one is going to be where we flip the stereochemistry, make our other exo, like so here. Okay, and then taking a look at this, we can do resonance. So I push these electrons downward. Puts it on a position that's not attacking. We want to push it down again to the bottom of our molecule. Taking a look at our dienophile here, we can push our electrons up, or I guess down in this case, to this carbonyl. Lining these two up. For our original structure, our charges are misaligned. Our second two options where we flipped it over, now our plus and our minus can come together. Making these two products our major, and most specifically our endo product, like so. All right, I'm going to talk about one more thing and then we're going to go, which is, we'll do some more of these on Monday. Different resonance possibilities. So there's not a lot of choices for your dienophile. It's pretty much always going to be a carbonyl here, which means it's always going to lead to a positive at this position, essentially opposite to where your carbonyl was. With the diene, there's two different places we can get resonance. So the one that we've been drawing is where it's coming off of this terminal position here. And it always ends up, I'm going to draw the resonance in one step. So we kick this down. Eventually we get down to here. There's another place we can get resonance where it's going to give us a different answer. And that's going to be off of this position. So if we put our OME here instead, when this pushes its electrons down, there's only one place it can go. And that's going to be this position. There's no way for it to get down to here. So from this point, now my negative is at the top of the molecule. I kind of box these out. Versus this top one where it was at the bottom of the molecule. So depending on where we locate this OME on our molecule, it can shift where our resonance is going to end up. So if we take the same example we just did, or let's take the first one. I'm gonna throw a methyl on here. A little far away. Now when we do this transformation, our four possibilities change a little bit. So we would get really bad ME. This would be an endo product. This would be an exo product. We could flip it over. Put in this carbon on the bottom. Or flip it over again. Or sorry, invert the stereochemistry to get our other exo product. Like so. Now when we do our resonance, so our dienophile is always the same. But then for our diene, we'll remove these electrons. They're going to end up on top here. So for this first structure here, this would be a charge misaligned because it's going towards a neutral end. Versus if we flip over our dienophile, now we can get a charge aligned species and lead to a product. So for this one, now that we move this over, our major product would favor these two, and specifically the endo product. Okay, I'm going to stop here. We're going to do a pretty big review of this on Monday, because I think this is a concept you need to hear a couple times before it really sinks in. So we'll probably spend the first half hour or so talking about this, maybe a little bit more. We'll also do it in Monday's recitation. And then there's another electrocyclic rearrangement that happens that we'll talk about for the last half hour of that class. But for the most part, this is what we'll be covering. So I will see you guys on Monday. Have a great weekend. And if you have recitation today, I will see you then.